born in fiery furnaces. It's the miracle material of spaceships and soda cans. Light enough to fly, but tough enough to hit a baseball. It can protect and preserve, or reflect and reveal the secrets of the universe. Stamped, melted, rolled, or even foamed, it has changed the world. Now, aluminum on Modern Marvels. There's a good reason the world devours nearly 100,000 tons of aluminum every day. And why the United States alone gobbles 25 billion pounds a year. Modern civilization couldn't survive without it. This strong, lightweight, flexible, rust-proof wonder is everywhere. An integral part of the planes we fly, the cars we drive, the structures of our cities, and the power lines carrying electricity to our homes. But most know it best when aluminum is no thicker than a human hair. It's found this way in over 95% of households as aluminum foil. Impervious to light, air, and moisture, it's perfect for preparing and preserving food.
There's nothing better for a barrier. Moisture protection, freshness, the deadfold characteristics that we use it to wrap our products is just, there's nothing better.
But how does it get so thin? And why is it shiny on one side and dull on the other? The Reynolds factory in Richmond, Virginia, maker of 340,000 pounds of aluminum foil every day, holds the answers. The aluminum arrives by rail car as massive 32,000-pound coils.
Once we receive the coils, they're unloaded off the rail car. We go into annealing ovens. The annealing process helps soften the metal so that we can further reduce it to the gauge and thickness that most people see in our standard Reynolds Wrap products.
Each sheet is 4.5 thousandths of an inch thick, about the same as a compact disc. Thinning the softened sheet is a job for the rolling mills, since the pressure they exert on the aluminum could create sparks and ignite fires. A cooling lubricant douses the sheet as it enters. Inside the mill, the sheet passes between a pair of powered spinning rollers. Larger, non-powered rollers positioned above and below them apply even pressure, helping them flatten the sheet in a uniform manner. One pass through the mill reduces the sheet thickness by half. It's also getting a lot longer, as the 3,000-yard long coiled sheet makes 6 passes through 3 different rolling mills.
When it finishes on our finishing mill, it's about 240 miles long because we've reduced it and increased the length.
This final pass through the finishing mill holds the secret to why aluminum foil is shiny on one side, but not the other.
So in order to support the metal and ensure we can pull it through the mill, we double pass it. We have 2 sheets of metal running through the mill at the same time.
Since the outer sides of each sheet contact the highly polished, lubricated roller surface, they emerge shiny. And since the inner sides touch only each other, they emerge with a matte finish. After the doubled foil exits, each single layer is only 6.4 ten-thousandths of an inch thick, 6 times thinner than a sheet of standard copier paper.
In this process, we're separating the metal from the double sheet to single sheet. The separation occurs at this point. One sheet is going to the upper rolls, the other sheet to the lower rolls.
As the sheets of foil separate, a set of knives behind this metal housing slices the roll into 6 equal divisions, measuring 12 inches across. Next, mechanical arms break apart the divisions, Now the foil is at its final thickness and width. Shortening each coil to the standard length happens at the packing facility. The coils run through a spooler that cuts each sheet and wraps it around a fiber core 300 times per minute. Machines then guide the cores into cartons, and the foil is ready to wrap food for the fridge, freezer, or grill all around the world. But does it matter which side faces in and which side faces out?
Actually, it makes no difference whether you use the dull versus the shiny side of the foil. They both are going to perform the same for cooking or freezing or storing with foil.
Aluminum foil's roots stretch back over 8 decades, when metals other than aluminum were preserving the goods that fed our sweet tooths and smoking habits.
It got its origins way back in about the 1920s when Reynolds Metals Company was in the business of producing lead and tin foil that was used in cigarette packaging. And they started wondering if possibly this protective foil could be made better and more economically by using the new metal called aluminum.
Aluminum arrived for home use in 1947. Touted as a new kitchen miracle, Reynolds Wrap debuted as a 25-foot-long, 12-inch wide roll, packaged in pink and silver.
Well, aluminum foil as a household foil was never made from lead or tin, and it's kind of interesting that people still refer to it sometimes as tin foil today.
But where does the aluminum used to make foil and a million other things come from? It's right beneath our feet, beckoning to miners as the most abundant metal in the Earth's crust. Out of every 1 million atoms in the ground, 82,000 are aluminum. But pure aluminum doesn't exist on its own in nature. It can be found locked away in reddish deposits of bauxite ore. The richest deposits of the ore exist in Australia, Guinea, Brazil, and Jamaica. A refining process will begin to extract the stubborn aluminum. A caustic soda digests the ore-rich dirt into a liquid and allows the separation of its components. The resulting white residue is then dried into a fine white powder, a compound called aluminum oxide, or alumina. This is the stuff from which aluminum is made. The trick now is isolating the aluminum from the oxygen. To pull that off, you need to transport the alumina to a production facility, like the one Alcoa operates here, near Evansville, Indiana.
We receive a barge every day into our ore dock. It's got roughly 3.2 million pounds of alumina on it, and we vacuum it out of the barge. It's basically like a large vacuum cleaner that you'd use at home.
The vacuum snorts about 300 tons per hour, emptying the barge in 10 hours and depositing the powder onto conveyor belts.
Actually, there's no smell to it at all. It's got a real granular feel to it. It's a little more coarse than what talcum powder is, more like salt.
Inside the 120-acre mega complex, 750 pots await the powder. Each contains a molten salt bath. Every 2 minutes, an overhead feeder dumps 7 pounds of alumina into one of the pots. As the powder begins to melt, the most critical component to isolating the aluminum takes charge. Electricity, and lots of it. The on-site coal plant delivers enough juice to the pots to power 300,000 homes. The electricity flows through copper rods connected to steel blocks suspended in the pot's salt bath. The aluminum oxide molecules filling the bath contain 2 aluminum atoms and 3 oxygen atoms. The electric current breaks the bond and forces the atoms apart.
And in that process, you're making liquid metal. The metal is a little bit denser than the bath. It settles to the bottom of the pot, and then carbon dioxide bubbles are given off.
But the process isn't over yet. Workers then have to extract the molten aluminum from the pots and turn it into a solid.
Crews literally vacuum the metal out in a process we call tapping. They use a large container. It's got a spout on it. We apply air to it and create a vacuum and suck the metal out of the bottom of the pot.
Forklifts then transport the crucibles to a holding furnace, where cranes lift and spill out the molten metal. Then channels direct it into casting chambers, where it will solidify. These hulking monoliths are destined to become everything from beer cans to boats, from saucepans to siding on your house. Not bad for a metal that's definitely the new kid on the block.
Well, the one thing to keep in mind is that aluminum is a fairly new metal. Bronze, lead, iron, copper have been around for centuries. Aluminum was first actually discovered as an element by a chemist, Sir Davy, in 1808.
But discovering this unique metal was one thing. Divorcing it from its ore compound was another. Throughout most of the 19th century, a variety of chemical processes could only generate impure samples in minute quantities. Aluminum was so rare, it was nearly twice as expensive as gold. In the 1880s, when advances in processing helped reduce its price, it was the fitting choice for engineers completing construction of the Washington Monument, who sought a precious capstone for their masterwork. The aluminum pyramid they placed atop the marble spire weighed 100 ounces. At the time, the largest piece of aluminum ever cast. 2 years later, in 1886, came the discovery that made aluminum accessible and inexpensive. Two scientists working independently, Frenchman Paul Héroult and American Charles Martin Hall, hit upon the chemical electric extraction process still in use today. Aluminum's market price plummeted to less than $1 per pound. The breakthrough unshackled the metal and triggered the rise of revolutionary new industries. Today, one of those industries crafts the aluminum that helps lift the most massive commercial airliner ever built. Producing new aluminum from recycled aluminum scrap requires just 5% of the energy needed to create it from raw materials. Aluminum will return on Modern Marvels, here on the History Channel. We now return to aluminum on Modern Marvels. This Goliath double-decker jet, the Airbus A380, is the largest commercial aircraft in the world. It stretches 10 feet longer and towers 16 feet taller than a Boeing 747. It weighs in at a whopping 1.2 million pounds. And like most commercial aircraft, 65% of that bulk is aluminum. It's a no-brainer that aluminum's lightweight makes it a perfect construction material for planes. But more important is its flexibility.
Aluminum is ideally suited for flying more than any other material. It's important that the material be able to withstand and give and take in those pressurizations and depressurizations that occur thousands of times over the life cycle of an airplane.
The wings of the A380, like any airplane, suffer constant stress. On the ground, they sag from their own weight. In the sky, the airflow required for lift pushes the wings in the opposite direction. The A380's pliable wings span over 260 feet and are comprised of the largest pieces of aluminum on the plane. 10 separate sheets case the surface of each wing, 5 on top and 5 underneath. They cover a series of aluminum ribs and spars, which form the skeleton needed to support the wing's length. The wing skins for the A380 are among the thousands of aluminum parts made here at Alcoa's Davenport Works Mill in Iowa. The plant is large enough to contain a golf course. Mill workers craft wing sections up to 112 feet long and weighing over 11,000 pounds. They begin with enormous 18-inch thick, 70-inch wide aluminum alloy blocks, weighing 30,000 pounds. The task of transforming each into a giant wing skin begins with this beastly rolling mill, measuring over 18 feet across, the widest in the world.
It's rolled along its longitudinal axis down to the proper gauge. Every pass, the top roll gets lowered, so you're squeezing that metal through a narrower slot.
Just like the raw sheets that become aluminum foil, the metal will get thinner and thinner and longer, until it is about 1 inch thick. Saws then cut each flattened plate to various shapes, depending on where they'll be positioned on the wing. Finally, twin milling heads refine and taper the pieces as necessary by skimming the plate surface.
We use 30-inch diameter cutter. It will generate this machine pattern on here that looks like swirls.
The completed wing skins are now ready for assembly by Airbus and other aircraft manufacturers. Flying with anything but aluminum seems almost inconceivable today. Yet plane-making pioneers fashioned the bodies of their crafts out of fabric-covered wood. But wood could rot and splinter. Seeking a more durable material following World War I, German designer Hugo Junkers was among the first to build planes sheathed in an aluminum alloy. In 1935, the Douglas DC-3 and its all-aluminum body ushered in the age of commercial flight. Sporting longer and larger wings than its predecessors, it could fly higher and faster. It could also carry more fuel, minimizing refueling stops. The duration of a coast-to-coast flight fell from an agonizing 26 hours to less than 18. And today, aluminum carries commercial travelers through the air for more than 800 billion miles every year. But planes aren't the only form of transportation revolutionized by aluminum. Each year, the automotive industry uses over 15 billion pounds of aluminum to make our cars. And with every year, it's using proportionally less and less steel. Why? Well, for starters, it saves gas.
Aluminum is significantly lighter than steel, and it gives you somewhere between 30 and 50% mass reduction compared to steel. And the general ratio is if you take 10% of the mass out of a vehicle, you can get up to about 8% of improvement in fuel economy.
Automakers prefer aluminum not only because it's the perfect diet pill for steel-heavy cars, but also because it's easier to melt and to shape. That's a big plus when it comes to casting the parts for the engine. That represents much of a car's weight.
What we've done here is take two crucibles. We filled one with aluminum and the other one with chunks of steel. We put both of these crucibles in a furnace and we set the furnace at 800 degrees centigrade.
No, it was more.
No, but it was blood. You can see that the aluminum is melted and the steel is still chunks of steel that are sitting there, maybe a bit red hot, but nevertheless not melted. This is one of the most critical and important attributes of aluminum, that it can melt at low temperatures, so we can melt it and pour it into cavities to make castings.
While this fluid wonder metal is helping cars lose weight under their hoods, it's also helping them get their bodies into shape.
It also allows you to make a lot of shapes that you couldn't make otherwise.
One way GM shapes its aluminum parts is with water, in a process known as hydroforming.
The reason we tube hydroform is we're able to form it in any particular shape that we need it without welding sections together. The hydroforming process allows us to make one part, and it is proven to be higher durability than you get out of two pieces welded together.
These water-shaped tubes will become part of the frame of a Corvette. Once a tube enters the die, high-capacity pumps flood it with up to 100 gallons of water. The resulting pressure helps the aluminum form into the precise shapes of the die. It's all over in less than 2 minutes.
I'm sitting in the Corvette body structure that contains aluminum hydroformed rails. These aluminum rails replaced steel rails that serve the same function but were heavier. This enables us to produce a Corvette that is lighter and has better 0 to 60 time than you would get with the steel version.
The pressure to shape aluminum car parts isn't restricted to water. You can also use air with a new technology known as QPF.
It stands for Quick Plastic Forming, which is not plastic. We're working with aluminum, but we take aluminum to an elevated temperature state in order to form parts in shapes that we can't normally form. In this operation, we're making the Cadillac STS trunk lid. The inner panel is just now coming out of the press, fully formed. What's coming in is the preheated aluminum sheet. As soon as that die gets closed, we use air pressure to force that aluminum up against that steel die cavity that gives us our shape.
QPF technology fashioned aluminum body panels for GM's fuel cell-powered concept car, the Sequel. Whether powered by hydrogen, battery, or hybrid engines, future vehicles must become lighter than ever to be competitive.
When you put a lot of money into the powertrain, like you need to do in those vehicles, it doesn't make sense to pull around a steel cage.
But aluminum is also a big hit in a different kind of cage, a batting cage. And one of the secrets to creating a bat that'll clean up against the competition is to give it one outrageously hot bath. In 1973, a car on the road in America contained an average of 81 pounds of aluminum. By 2006, the average was 319 pounds. Aluminum will return on Modern Marvels. We now return to aluminum on Modern Marvels. A wood bat is the foundation of professional baseball, and has been since before the days of the Babe. To maintain that tradition, pro players can't use anything else. But aspiring pros aren't required to use wood. In fact, more than 90% of all bats sold today are made not from wood, but aluminum. The reasons are obvious. First, bats made from aluminum are lighter, enabling players to generate more bat speed as they swing. Unlike wood, aluminum can be strategically balanced along the length of the bat, allowing it to channel vibrations and transfer energy more efficiently. As a result, on contact, baseballs fly up to 20 feet farther. And the bat's sweet spot, the ideal hit zone, is larger. They debuted at the collegiate level in 1974 and forever altered the nature of the game.
by 1976, the batting averages for NCAA had climbed 30 points. So there was the big difference in terms of just simply putting the ball in play.
The Anderson Bat Company in Orange County, California, one of the few remaining American bat makers, crafts 300 aluminum bats every day. The simple shape of the aluminum bat masks the precise science behind its creation.
The aluminum has the strength-to-weight ratio that is probably the most advantageous of any of the metals.
Anderson makes its top-of-the-line bat from an aluminum alloy with a touch of zinc that adds toughness and durability. The process begins with 17-foot-long hollow aluminum tubes. An operator saws the tubes to lengths ranging from 22 to 26 inches, depending on the final bat model. Then it's up to a machine called the rotary swedger to reshape each tube into a precisely molded and balanced bat. The aluminum fits over a mandrel bar as it enters the swedger between a twin pair of dies. As the tapered die halves rotate, they open out. A series of spinning rollers, positioned around the perimeter, shove the dies back and close them. The rotation opens and closes the dies 1,500 times per minute. As the aluminum feeds into the swedger, it's forced to take the shape of the narrowing die cavity. The aluminum needs 3 passes through the rotary swedger. Each pass thins the wall and elongates the tube. The final pass tapers the handle.
This is the cut stock. This is what you saw earlier, and it's 26 inches long. This one is a first pass. It's the thinning stage of it. This is a second thinning stage, and you can see that as we go and thin, the tube gets longer. And then this is the final pass, and while this is 26, this is 41 inches long.
These bats may now be expertly shaped and balanced, but before they can punish baseballs, they have to be hardened. This happens just a few miles away, at a facility where a hot bath waits to heat treat the aluminum. The bath doesn't hold hot water, but rather sodium nitrate. Unlike water, the salt solution won't corrode the aluminum.
Heat treat is a 2-step process. An elevated temperature for a certain amount of time, and then a rapid cooling called a quench. It's kind of exciting because you go from this salt bath to a water tank. You have to do it with less than 15 seconds.
The rapid cooling following the elevated temperature soak creates microscopic particles in the aluminum, which strengthen the metal. After the bats bake in an oven to preserve their hardness and shape, an inspector checks each one to see if it's a hit or an error.
What we're looking for is a range. If it's too hard, the aluminum can crack, and if it's too soft, obviously it will dent.
After the inspection, workers at another facility add the graphics and color. And workers back at Anderson Bat Company apply the finishing touches. An end on the handle, a cap, and the grip. How does this finely crafted aluminum bat compare to one made of wood?
What we're measuring is the velocity of the ball off of the bat from the tee. And the radar gun actually picks up the very fastest point of the ball between the tee and the gun. And we're going to start with the wood bat. Okay, that's 86 miles an hour. 85.
And now the aluminum bat.
91. 91. Wow.
If, say this point right here is my ideal hit zone, where I'm going to get my best performance, with an aluminum bat, the size of that hit zone is going to be larger than with a wood bat. So say the wood bat is going to be the size of a baseball. Your aluminum bat's going to be double that. It's going to be the size of 2 baseballs. So the chances of me getting better performance when I miss-hit a bat is going to increase as opposed to using a wood bat.
Will aluminum bats ever graduate from college to the pros? Don't hold your breath.
Baseball is a very traditional sport, and wood, the crack of the bat, and all of that is very much a part of the fabric of baseball. At the same time, if you were to put an aluminum bat in the hands of professional players, you would have to change all of the records. They'd have to be asterisk.
Ball players aren't the only ones reaching new heights with aluminum. NASA is using it to gaze into the deepest reaches of the universe. At the point of contact, an aluminum bat generates up to 4 tons of force on a baseball thrown at 90 miles per hour. Aluminum will return on Modern Marvels. We now return to aluminum on Modern Marvels. In 2016, a new telescope called the Giant Magellan, the world's largest, will begin peering skyward from an observatory in Chile. A cluster of 7 mirrors, more than 80 feet in diameter, will redirect so much light from the heavens to astronomers' eyes. It will produce images up to 10 times sharper than the Hubble Space Telescope. It will allow astronomers to study newly discovered black holes, stars, and galaxies. But the Giant Magellan wouldn't see anything without aluminum coating each mirror. Your mirror at home uses a layer of silver, and it's actually slightly more reflective than aluminum. But astronomers use aluminum for their telescopes because it's more durable and less expensive to maintain. Making aluminum-coated mirrors for telescopes isn't as simple as dipping a brush in buckets of aluminum paint and slapping it on glass. Just ask the scientists at NASA's Goddard Space Flight Center in Maryland. The setting for the transformation of glass into mirror is a vacuum chamber.
The process of coating the mirror demands that the environment not be contaminated. We actually evacuate most of the air out of the chamber. So the cleaner the chamber is, the cleaner the coating is going to be.
With the glass in place, it's time to add the aluminum.
These staples are 99.999 pure aluminum. We use these as the base for the aluminum coatings. We put them on by hand on the tungsten filaments to prepare it for the coating process.
The lid lowers, sealing the chamber, and a pump removes virtually all the air. An electric current heats the filaments, melting the staples and removing any lingering impurities in the aluminum.
Once the aluminum is melted, this is the way it looks on the filament. So you can see that the aluminum is no longer a hard staple, but it's actually wetted along the coils of the filament.
Next, a second, stronger electric current passes through the filaments. In a blinding flash, the aluminum vaporizes. The hot aluminum gas rises and condenses on the cooler glass surface. The deposited layer is 1,500 times thinner than a human hair. But as shiny as the aluminum coating is, it faces a host of enemies.
Over time, moisture and pollen and bugs and things like that will get on the optical surfaces, and they'll start etching into the aluminum, and they degrade the coating over time.
The only way to restore an aluminum-coated mirror is to remove the corrupted coating and replace it with a fresh one. It's a major event for observatories and a necessity about every 2 years. First, technicians must remove the mirror from the telescope's housing. Stripping off the old coating starts with soap and water. Chemical solvents then eat away the aluminum coating to reveal the underlying glass base. Next, paper towels are used to clean and dry the glass before a vacuum chamber lowers into place and deposits the shiny aluminum. Bugs and dirt aren't a worry for the orbiting 95-inch aluminum-coated mirror on the Hubble. But NASA engineers have to guard it against an entirely different threat.
You go up in space and you have extreme differentials. If it's facing the sun, if it's nighttime, you're talking hundreds of degrees in variation, and that'll change the contour of the mirror.
Trying to lick the problem, NASA scientists have developed a new kind of aluminum mirror without a glass base.
You can use the aluminum to make your mirror and the mounting structure all out of the same material. If the temperature changes, then your mirror and your mounting structure then shrinks or expands by the same amount. So you don't get distortions and stresses that will twist the mirror and destroy its imaging properties.
The challenge for NASA's engineers is to turn pure aluminum discs like this one into mirrors. Pulling that off requires getting rid of the rough surface. A diamond-tipped lathe is the answer. It will dig in just below the surface and in a uniform slice begin to smooth the aluminum to a natural shine. During the procedure, a paint thinner solution sprays away debris. It also cools the diamond tip, which heats up as it carves into the metal. And after just 2 minutes, a final polishing treatment will smooth out leftover microscopic imperfections. NASA scientists speculate that pure aluminum mirrors like this could someday replace the more common aluminum-coated glass mirrors. Of course, NASA's love affair with aluminum isn't just limited to mirrors.
Anything you want to lift off the surface of the Earth, you're fighting gravity. So you want to look for materials that are very lightweight and strong and take advantage of other properties. Reducing the mass to take it to orbit is a big deal. Every pound, every ounce counts. So the aluminum has a perfect combination of many of the characteristics we look for. It is very lightweight, it's malleable, meaning that you can work with it easier, it doesn't corrode. It's easy. If you look around anywhere in NASA, you will see it being applied in just about everything we do.
And it's been that way for over 5 decades.
It has been one of those materials that actually have made many of the things that we're doing now possible.
As aluminum continues to help us explore new worlds, it may also prevent terrorist bombings from leveling our buildings. This spongy new wonder could save your life. The space shuttle is not only made from aluminum, but also fueled by it. Each of its twin rocket boosters requires 1 million pounds of fuel, 16% of which is solid aluminum powder. Aluminum will return on Modern Marvels. We now return to aluminum on Modern Marvels. 1983, Beirut, the United States Embassy Building. 1995, Oklahoma City, the Alfred P. Murrah Federal Building. 1998, the United States Embassies in East Africa. The structures in these attacks proved no match against a devastating explosion unleashed by a powerful bomb. But these buildings may have fared better had they been clad in an innovative form of aluminum produced by Canada's Cymat Technologies. They call it aluminum foam. Its unique sponge-like structure could prove to be a lifesaver around the globe.
The foam basically absorbs the shock wave so that there isn't such a severe impact. And so if you had blast protected the concrete columns supporting the structure, there's an excellent chance that the buildings wouldn't have collapsed and a lot of lives would have been saved.
Aluminum foam's key ingredient is nothing more than air. But the real trick to making it isn't injecting air bubbles into the aluminum. It's keeping the bubbles intact once they're inside.
Our material is molten aluminum with ceramic particles in it. Those particles stabilize the bubbles, in other words, stop them from popping. And a good example of this is if you've ever tried to use dried cocoa powder and mix it into milk. And as you're doing that, you see this froth forming on the surface with the dried cocoa on the bubbles. The bubbles are stable.
Cymat begins its production process by melting down aluminum bars, already containing the ceramic particles. The furnace holding the materials spills a scalding stream into a channel, leading to a receptacle called the foaming box. Now it's time for the all-important air. Inside the foaming box, a nozzle injects air, creating bubbles in the molten concoction. More air creates a less dense and lighter final product. A propeller at the end of the nozzle keeps the ceramic particles evenly distributed. The bubbles rise, and as they reach the surface, begin to cool and harden.
When it gets to the top of the foaming box, it's already starting to solidify. So it curves up onto the belt and goes into the press, and that takes a lot of the heat out very quickly to solidify the cells and give you the solid panel.
The emerging half-inch thick panels measure 4 by 8 feet. Solid aluminum this size could weigh more than 300 pounds. But each of these panels weighs only about 30 pounds. Foamed aluminum can also be injected into a three-dimensional cast. What looks like a heavy chunk of metal is actually light enough to float in water. A view of the casting skeleton shows why.
In the X-ray machine, we have a part that from the outside looks like a solid aluminum casting. We're looking right on the edge of the part. You can see a dark line here where we're actually looking down the edge of the casting. But if I rotate this, you can see the cellular structure. There's a lot more air there than there is solid material. The cellular structure allows it to collapse and absorb energy. Imagine each one of these little bubbles is breaking, these cells is breaking as the part is crushed, and there's energy being absorbed by every one of those walls collapsing.
The idea of a light, formable, shock-absorbing metal is gaining the attention of not only government officials, but also automakers. It may allow cars to shed weight without sacrificing passenger safety.
One of the applications for this product is crash boxes in automobiles. Crash box is the element in a bumper system which absorbs the energy in a low-impact crash. We take a normal hollow aluminum extrusion that might form that crash box, and we insert aluminum foam inside the product and then crush it as it would be crushed in a crash. It does two things. It absorbs the energy, and it also forces the aluminum extrusion to create many folds, and every one of those folds absorbs energy.
Aluminum foam is just the latest incarnation of this invaluable metal.
A world without aluminum, perhaps I'm biased, but for me it's unimaginable.
A century before it helped carry man to the moon, Jules Verne hinted at its vast potential, describing it as having the whiteness of silver, the indestructibility of gold, the tenacity of iron, and the lightness of glass. But even that great visionary couldn't have foreseen the scope of aluminum's many modern applications.